Good morning, everybody. Hope you're all healthy and safe. So let us continue with our section 4.2. So in the last lecture, we were discussing about inverse Laplace transform. We had done few problems related to find the inverse Laplace transform of various functions, and we had also seen some inverse Laplace transform of some basic functions which you could find out easily. So now in this lecture, what we'll be discussing is that in the very beginning, in the beginning of this section, I had just mentioned that we'll be using Laplace transform to solve the differential equations, right? So far we know few methods to solve the differential equation, but Laplace transform also plays an important role in solving the differential equation in a simple manner, apart from the partial fraction and solving thing. For that, for solving the differential equation, we'll be using both Laplace transform as well as the corresponding we'll be using the Laplace transform of a derivative and the inverse Laplace transform. So before moving on to the solution part, I think we'll have to discuss about the Laplace transform of the derivatives. Okay, so we shall begin today's session with that is transform of derivatives. There is a theorem that is if f dash etc f raised to n minus 1, these are the derivatives, are continuous on the interval 0 infinity, and they are of exponential order. Now all of you must be familiar with what is meant by exponential order. And if fn of t, that is the nth derivative of the function, is piecewise continuous, then the Laplace transform of nth derivative of f, that is script L of fn of t, is nothing but equal to s raised to n into f of s, capital F of s, where f of s is nothing but L of f of t, minus s raised to n minus 1 into f of 0 minus s raised to n minus 2 into this must be s raised to n minus 2. There is a slight mistake. Okay, this is 2. The power keeps on decreasing. Okay, s raised to n minus 2 f dash of 0 etc f raised to n minus 1 of 0. Okay, so this is the transform of a derivative. So since we are solving differential equations, clearly it will contain derivatives, so differentials, so we'll have to know what is the Laplace transform of that differential. So it is given using this formula. I'm just going to repeat it again. The Laplace transform of the nth derivative of the function is nothing but s raised to n into capital F of s, where capital F of s is nothing but script L of f of t, minus s raised to n minus 1 into f of 0 minus s raised to n minus 2 into f dash of 0 etc minus f raised to n minus 1 of 0. Okay, so we'll just see how this concept has come, or how to solve this, how did this theorem come into existence. It is just by the proof that we can easily prove that. Let's see how we can do that. So we need to find what this. First we shall determine the Laplace transform of f dash of t. Okay, so if you all remember, the formula is nothing but 0 to infinity e raised to minus st into the function. So here the function is f dash of t dt. So both the terms contains the variable t, so we'll have to use integration by parts. So by integration by parts, what is integration by parts? In integration by parts, what we do is we'll have to consider the first function and the second function. So here the first function will be e raised to minus st, and this will be our second function. So by integration by parts, this is nothing but first function into integral of the second function, okay, minus integral of derivative of the first function into integral of the second function. So So this is nothing but e raised to minus st, integral of derivative, that becomes the function itself, f of t, varying from 0 to infinity, minus integral 0 to infinity. What is the derivative of e raised to minus st with respect to t? It is e raised to minus s into e raised to minus st, and this is integral derivative, that is nothing but f of t itself. So this is nothing but e raised to minus st into f of t, varying from 0 to infinity, minus minus plus s into integral 0 to infinity e raised to minus st f of t. Okay, so when we apply limit over here, e raised to minus infinity is 0, so first term is 0, minus of e raised to 0 is 1, so we get f of 0. So this will be equal to, the value will be equal to e raised minus f of 0 plus s into, the term we had was 0 to infinity e raised to minus st into f of t, that is nothing but the Laplace transform of f of t, or I can write this as minus f of 0 plus s into capital F of s. Okay, so I get the Laplace transform of f dash of t is nothing but s into f of s minus f of 0. Okay, so like this, if we proceed, if I move on to finding the Laplace transform of the second derivative, that is script L of f double dash of t, what will be this value? This is nothing but integral 0 to infinity e raised to minus st f double dash of t dt. So this will be minus e raised to st into f dash of t, no, now minus plus, varying from 0 to infinity, and plus s into integral 0 to infinity. Here also again we will be applying the integration by parts and solving it. Okay, so the first term will become minus f dash of 0 plus s into L of f dash of t, right? So this is minus f dash of 0 plus, what was L into f of t? It was s into f of s minus f of 0. So we get altogether, this is s square f of s minus s into f of 0 minus f dash of 0. Okay, so I hope you are getting the point. If we do this again continuously, we will get the derivative of the Laplace transform of the nth derivative, which is given in the theorem, that is Laplace transform of fn of t is nothing but s raised to n f of s minus s raised to n minus 1 f of 0 minus s raised to n minus 2 f dash of 0, and so on, etc., minus fn minus 1 of 0. So this is the Laplace transform of derivatives. Now with the help of this transform of derivatives and the inverse transform, we will be able to solve the differential equation. So I'll just show an example how to do that, and then we shall move on to a new theorem. So we are asked to solve the differential equation dy by dt plus 3y is equal to 13 sine 2t, given y of 0 is 6. So this is actually an initial value problem, because the initial value is given to us, and also this is in a very familiar form, dy by dt plus py is equal to, here p of t, instead of x we have t, so p of t is 3 and q of t is 13 sine 2t. So we know how to solve this by using the integrating factor method, but I'll show how to solve this with the help of Laplace transform. Okay, so when we apply, I'm going to apply Laplace transform on both sides. Applying Laplace transform on both the sides. What do we get? Script L of dy by dt plus 3 into script L of y, okay, is equal to 13 into script L of sine 2. So here y is actually depending on t, so y is some function on t. Okay, so this is nothing but L of y dash of t plus 3 into, to just make it a little bit more clear. Okay, otherwise we'll get confused by Laplace transform for y is nothing but as L of t, but it is not, because y is a function which is depending on t. So y actually plays a role of f of t here. Okay, into script L of sine 2t. So now I think it's a bit more clear. So what is the Laplace transform of the derivative? Just now we have seen it is nothing but s into, instead of f of s we have y, so y of s minus y of 0 small y of 0, that is plus we have 3 into, this is again y of s is equal to 13 into, what is the Laplace transform of sine 2t? It is nothing but 2 divided by s square plus 4. So this is 26 by s square plus 4. Okay, this is the Laplace transform of derivative, and this is L of y of t is nothing but capital Y of s. Okay, so we will get an equation in terms of y of s, right? So we get s plus 3 combining the terms of capital Y of s plus 3 into y of s, minus y of 0 was given us to be 6, right? This is equal to 26 by s square plus 4. So this implies s plus 3 into y of s is equal to 26 by s square plus 4 plus 6. So what will be y of s? Y of s will be nothing but 26 by s square plus 4 into s plus 3 plus 6 by x plus 3. So this is nothing but 26 plus 6 into s square, taking the LCM, by s square plus 4 into s plus 3. Okay, right? So we have got the expression of y of s. Further simplifying, I get y of s is nothing but 6s square plus 50 whole divided by s plus 3 into s square plus 4. Okay, so this again, if we apply the inverse Laplace transform, we will get the value of y, and actually y is the solution of the differential equation, right? So to get the value of y, we'll apply the inverse Laplace transform. Okay, so here if we have to apply the inverse Laplace transform, we have to transform it into some common or basic form. So for that we have to apply, we have to use the partial fraction method. So let us see how we can do that. So we write 6s square plus 50 by s plus 3 into s square plus 4 is nothing but, so here we have a quadratic factor, so we'll have a by s plus 3 plus b s plus c divided by s square plus 4 corresponding to the quadratic factor. So this implies again the denominator taking LCM, I get this is taking LCM and equating the numerator part because the denominator is c. A into s square plus 4 plus bs plus c into s plus 3. So substituting suitable values of s, we can find or we can determine the value of a, b and c. Okay, so when s is put s is equal to minus 3, so this term becomes 0, and this implies we get 6 into 9 plus 50 will be equal to 8 into 9 plus 4. So this implies solving I get a is equal to 8. Okay, now what we do is we equate the coefficients of s square. Okay, so to find b and c. Okay, so here we have a s square, I'm just expanding it, okay. S square plus a into 4 into a plus b into s square plus 3bs, just opening up the bracket, cs plus 3c. Okay, then what I do is I compare the coefficients of s square. Okay, so comparing the coefficients of s square and s, what do I get? S square coefficient is a plus b is equal to 6. Now if I take the coefficient of s, on the left hand side it is 0, so on the right hand side we have 3b plus c, right? 3b plus c is equal to 0. So a plus b is 6, a is 8, so this implies what do we get? I get b is equal to minus 2, and since b is minus 2 and 3b plus c is equal to 0, I get c is equal to 6. So I have got a, b and c. So let us write what will be our y of s. So y of s will be now nothing but 8 by s plus 3 plus b is minus 2 minus 2s plus 6 by s square plus 4. Now I am going to apply the inverse Laplace transform. Okay, inverse transform, what do I get? Script L inverse of y of s, right, that is equal to script L inverse of 8 by s plus 3 plus, here I'll apply the linearity also, so it will be minus 2 into L inverse of s by s square plus 4 plus 6 into L inverse of 1 by s square plus 4, right? So what will be this value? The script L inverse of y of s is nothing but y of t, which is the solution of the differential equation, and the script L inverse of 1 by s plus 3 is nothing but e raised to minus 3t, and we have minus 2 into script L inverse of s by s square plus 4, that is nothing but cos 2t, and we have 6 into script L inverse of 1 by s square plus 4. So to make it into a familiar form, we'll have to multiply and divide by 2, so we'll get L into sin 2t. So this is the solution of the differential equation initial value problem which was given to us. So as you have seen, we have applied both the method, both transforms, that is, one was the linear transform, Laplace transform as of the derivatives, as well as we have applied the corresponding inverse transform which we have discussed in the previous class. So this is the method in which or by which we can apply or we can solve a differential equation. Again, I'm mentioning we have learned different methods to solve the differential equation. If we are asked to solve using Laplace transform, we'll have to follow this method, that is by using the Laplace transform of the derivative and then finding the value of y of s and then applying the inverse Laplace transform. Okay. So now we shall just discuss one small theorem and we shall wind up with this section. So there is a theorem 4.2.3 that gives us the limiting condition of the Laplace transform of a function. So if the function is piecewise continuous and of exponential order, then the limit s tends to infinity, script L of f of t is nothing but 0. Okay. So with this we shall wind up the section, that is just we have to do the problems, or we shall be discussing more problems related to solving the differential equations. So that's it. Thank you. Stay safe and stay healthy.